Differentials and linear approximations. Why do we need differentials? Sometimes we are interested in determining the effect a small change to the input of a function has on the output of the function. For example, we know the cube root of 27 is 3, but approximately how much larger is the cube root of 27.2? So we are increasing the input by a small amount, by 0.2, how is that going to affect the output? Here we have that a pizza company claims to make pizzas with an 18-inch diameter. If the diameter is less by a half an inch, approximately how much pizza are they shorting you? To answer these questions, we are going to introduce the notion of differentials. Let's dive into differentials. Given a differentiable function, y equals f of x, the differential dx is an independent variable which represents the change in x, and the differential dy is the approximate change in y. Let's go ahead and take a look at a couple graphs and try to understand the idea behind the actual change in y, which we're going to call delta y, and then we'll talk about the approximate change in y, the differential dy. So starting on this first graph here, we have our function f of x, and we have a point on f of x. This is the coordinate point a f of a. So now, if we move a small distance away from a, let's call that distance dx or delta x. Those are interchangeable. That is a small change in the x value moving away from a. So the actual change in y is going to be found by going over to this new x value, a plus dx, going up and finding the function. So this is the coordinate point, a plus dx, f of a plus dx. So the actual change in y is subtracting these output values. So f of a plus dx minus f of a. So this distance here, delta y, is equal to f of a plus dx minus f of a. I'm subtracting the two y values. So that's the actual change in y. So I'm on the function at a f of a, I'm on the actual function at a plus dx, f of a plus dx. So this small change in x here led to this actual change in y, this delta y value, found by subtracting the two y values, the two output values of those two coordinate points. Well, that assumes that we have the actual function f of x, and we're able to calculate f of a and f of a plus dx. But sometimes we don't have the actual function or can't compute it, so instead we're going to settle for the approximate change in y, and that's this idea of the differential. So the differential relies on a tangent line. So the differential dy is defined to be f prime of x dx. And this should actually be pretty familiar. We're used to seeing dy dx is equal to f prime of x. So what's happening here is now we're thinking about dy dx as the numerator, the approximate change in y, over a denominator, the approximate change in x. So we're essentially now thinking about this as a fraction, and we're thinking about multiplying the dx to both sides, so that we end up with this idea of the change in y, dy, equal to f prime of x dx. And we'll take a look at this on a graph. So here's our function again, f of x, and here's our point on the graph, a f of a. And now we notice that that is a point of tangency. So we have a tangent line drawn right at a f of a. So from that tangent line, the slope of the tangent line, of course, is dy dx, or f prime of x. So we can see this rise dy over this run dx. So the slope of the tangent line, f prime of x, is the same as dy over dx, rise over run. So here, now, dy is this approximate change in y. So we're interested in the actual change in y. Like we said over here, subtracting the actual y value outputs. But if we can't find that specific point that's corresponds to, a plus dx, we'll settle for instead using the tangent line and finding this approximation for delta y, finding this distance here, this dy. So note, as I mentioned, dx is equal to delta x. So this distance here on the x-axis, dx and delta x are interchangeable. But dy is approximately delta y. Ideally, we would want delta y, the actual change in the y values if you change the input on the x-axis, but we'll settle for dy, the approximation, using the tangent line. So we use differentials when we want to study the change in a function. Let's look at an example. Here we're given the function y equals the square root of x, and in part A we're asked to find dy. So as a reminder, dy is equal to f prime of x dx. So the first step is really going to be to take the derivative. So remember, square root of x, that's x to the 1/2. So if we take the derivative, dy dx, that's 1/2 x to the negative 1/2, or 1 over 2 times the square root of x. But now we want to solve for just the approximate change in y. So dy we can isolate by multiplying by the change in x, multiplying by dx. So we have dy is equal to 1 over 2 times the square root of x times dx. Now let's move on to part B. We want to calculate dy, so the approximate change in y, and delta y, the actual change in y, when x is equal to 1 and the change in x is equal to 0.1. All right, so now here we already found what dy is equal to, 1 over 2 times the square root of x times dx. So we're really just going to go ahead and substitute in our value, x is equal to 1, and our tiny change in x, which is 0.1. So we're going to calculate dy is 1 over 2 times the square root of 1, and then times dx, which is 0.1, or 1/10. So here what we have is we have 1/2 times 1/10, and that's 1 over 20, which as a decimal is 0.05. So this is the approximate change in y. When you start at an x value 1 and you change x by a little bit, you increase it by just 1/10. It turns out that the corresponding approximate change in y is 0.05, or 5/100ths. So now let's figure out, well, what's the actual change in y? What is delta y? And to calculate that, we have this formula here, f of a plus dx minus f of a. We're going to have f of 1 plus 0.1, so that's a plus dx, so the value of 1 plus 0.1, and then minus f of 1. So this is f of 1.1 minus f of 1. So y is equal to f of x, so we plug 1.1 into the square root of x. So we're looking at the square root of 1.1 minus the square root of 1. So we're going to need a calculator for this. So that means it's going to end up being approximately 0.0488. So it's not too far off using the differential to approximate versus the actual change in y, which we needed a calculator for to get the square root of 1.1. Now let's make sure we understand graphically what we just found. So in part C, we're going to sketch y equals the square root of x, the dy and delta y you found in part B. So we're going to graph the square root of x function, which only exists in quadrant 1. So it starts at the origin, and it's this increasing curve here. And the x value that we're concerned with is x equals 1. So when we plug in 1, we get out 1 on the square root of x function. So we have the coordinate point 1, 1. And there I'm going to draw a tangent line as best I can here. All right, so now we want to sketch dy versus delta y. So I'm gonna fudge it a little bit here, because what we want to do is analyze when I'm a distance dx away. Well, dx is very small. Dx is 0.1, because we're talking about making a small change in x to see what happens to the change in y. But I wouldn't have a very visible dy or delta y if I make 0.1 as small as it actually is. So 0.1 would be really close to 1. So like I said, I'm kind of going to like fudge it a little bit, and I'm going to put 1.1 way over here. So this distance here, this is my dx, this is my delta x, this is 0.1. Let's start by finding the actual change in y. So this is the 0.11. If I go to 1.1, then let's go ahead and find y of 1.1. So that would be actually on the curve, square root of x. So delta y is the actual change in y values. So we're looking at this little distance here. So this little distance is my delta y. So we had this little distance here was our delta x or our dx, and this is our actual change in y. The approximate change in y is the rise part of rise over run in the slope of the tangent line. So for the rise part, I'm looking at this part right here. This is my dy, and then this is my, again, my dx. So rise over run, that's the slope. Dy over dx, that's f prime of x, the slope of the tangent line. So this is dy, so we have that was 0.05, and then delta y, that was that 0.0488 approximation. Let's look at another example. This was actually one of the introductory problems. We know that the cube root of 27 is exactly 3. So in part A, we're asked approximately how much larger is the cube root of 27.2. In other words, calculate dy. So here we're making a small change to the input, where instead of inputting 27 into the cube root function, we're inputting 27.2. So a small change to the input, we want to know approximately what's that change to the output. So let's start with a few things. Let's identify the function that we're working with. So it's going to be the cube root of x. So y is equal to the cube root of x, or x to the 1/3. The a value. So the value that we can evaluate is 27. So that's going to be the point of tangency. So a is going to be 27. And then that change in x is going to be 0.2, positive 0.2. So we started with 27, and then we're making a small positive change to 27.2. So we call that our dx or our delta x. Those are the interchangeable. So that's 0.2. So now that we have this information, let's calculate dy. All right, well, let's start with dy dx. So that would be 1/3 x to the negative 2/3. And so now we're going to multiply the dx to the other side. So dy is 1/3 x to the negative 2/3 dx. And now we can plug in our x value, our 27, and then our dx, our 0.2. So we're going to have 1 over 3, and then we're going to have 27 to the 2/3 times our dx, which was 0.2. So let's go ahead and evaluate 27 to the 2/3. So the easiest way to do this is to think about it as first the cube root of 27. So we're thinking about the cube root part first. The cube root of 27 is 3, and then we'll handle the squaring it part. So 3 squared is 9. So 27 to the 2/3 is just 9. So we have 1 over 3 times 9, and then 0.2 is 2/10 or 1/5. So if we multiply this all out, we end up with 1 over 135, or approximately 0.0074. So it looks like if we change the input of the cube root function from 27 to 27.2, the output is going to change by 0.0074. So now we can answer part B, which is to use your answer in part A to approximate the cube root of 27.2 using the differential. So the idea is that the cube root of 27.2 is approximately, well, the cube root of 27 plus my differential value that I just found, 0.0074, or 3 plus 0.0074, so 3.0074. And finally, we want to use our calculator to figure out what this value actually is, and then the actual change in y. So the cube root of 27.2 with a calculator is approximately 3.007389. So pretty close, right? So what is the actual delta y? So the actual delta y is computing the cube root of 27.2, the difference in the output of the cube root of 27.2 and the cube root of 27. So that difference there is approximately 0.007389. So it's not too far off from our approximate change in y, dy, 0.0074 versus 0.007389. Now let's look at our other starting example. Suppose a pizza company claims to make pizzas with an 18-inch diameter. In part A, how much pizza should you be getting? So let's start by calculating the area of the pizza. So the area of a circle is pi times the radius squared. If the diameter of our pizza is 18 inches, then that means that the radius of our pizza is 9 inches. So our area is going to be pi times 9 inches squared. So that's going to be 81 pi inches squared. So that's the exact answer. Let's go ahead and approximate that answer. It's approximately 254.469 inches squared. So that's how much pizza we should be getting. But in part B, we're told if the diameter is less by ½ an inch, how much pizza are they shorting you? So we want to calculate the error. We're told that the diameter is less by ½ an inch. So that means that the change in the diameter is negative. Since it's less by ½ an inch, we're changing the input, but we're making it smaller. So it's going to be a negative 0.5 inches. But our formula that we have dealing with area is in terms of the radius. So we're going to need to figure out the change in the radius, and the radius is always half the diameter. So the change in r, delta r or dr, is going to be negative 0.025 inches. So let's go ahead and now find the differential dA. So the error is the approximation for the change in A. So we have if A is equal to pi r squared, then dA dr, so the derivative of the area function with respect to r is 2 pi r. And we just want dA, and so that's going to be 2 pi r times dr. So I'm going to multiply that dr to the other side. So to calculate the error, right, the change in the area, we're going to go ahead and substitute in our value for r that it should be, so that was 9 inches that it should be, and then times that change in r. So that's delta r, or again dr, those are interchangeable. So we have 2 pi times 9 times negative 0.025. And if we multiply all that out, so exactly, this is 9/2 pi inches squared, but approximately this is negative 14.137 inches squared. So we know that we were being shorted, so we know we have a negative amount here, right? So is that a lot of pizza, right? So the diameter was only less by 1/2 inch, or the radius was only less by 0.025 inches. So I'm getting shorted, 14.137 inches squared of pizza. I'm supposed to be getting, right, 254.469 inches squared of pizza. So is that a lot? That brings us to part C, calculating the relative error and the percentage error. So error doesn't really mean as much unless it's in the context of what we're actually getting. So if we're talking about being off by a centimeter when we're measuring the length of a football field, that's not really a big deal. But if we're off by a centimeter when actually creating the football, which is a lot smaller, that's a bigger deal. So we're going to go ahead and calculate the relative error, which is the error divided by the actual value. So whenever we do a calculation, if possible, we don't want to use a rounded previous value. So to do this computation, the error that we're going to use is the negative 9/2 pi value, not the approximate value. And the actual value we're going to use is 81 pi. So we're going to have that our relative error is equal to negative 9/2 pi divided by 81 pi. So pi over pi is just 1, so that's going to cancel. And so here we're going to end up with negative 9/2 times 1 over 81. And so 81 and 9 can simplify. So we end up with negative 1 over 18, which is exactly negative 0.055. So that is what we call the relative error. And the percentage error is taking that value and multiplying it by 100, turning it into a percentage, which means really just taking the decimal and moving it 2 places to the right. So the percentage error is going to be negative 5.5%. And so that kind of gives us a better idea of just how much pizza they're shorting us. So maybe just looking at this numerical value didn't really tell us too much, like, is that a lot? But now you can see they're shorting us a little more than 5% of pizza by being off in the diameter by 1/2 inch. Now let's move on to the second part of the lesson, which is about linear approximations. Before we dive into linear approximations, we're going to look at the idea of what we call local linearity. We say a function is locally linear at some x value a if the graph looks more and more like a straight line as we zoom in on the point a f of a. So here we have 2 different graphical examples. So here we have this function. that right at x equals 1, we would consider this function locally linear. So if we were to just continue to just zoom in tighter and tighter and tighter around this value at x equals 1 on this curve, it would basically end up looking like a line as I continue to zoom in at that value. As opposed to, on this absolute value function, right at x equals 0 specifically, it doesn't matter how much I zoom in on this function, right at x equals 0, it's never going to look like a line. It's going to still look like this little v at the corner there. So that brings us to this theorem that says if the derivative exists at this x value a, then f is locally linear at x equals a. So right at x equals 1, we can see we have a differentiable function. So if the function is differentiable at x equals a, then when you zoom in on it, it's going to look like a line. So basically, we're going to be focusing on differentiable functions. So why do we study and use linear approximations? Because lines are nice functions. So we want to use lines to approximate nonlinear differentiable functions. So imagine we have this curve here. It's a differentiable function. We're going to create a tangent line, and we're going to use that tangent line to approximate values on the function itself near that point of tangency. So as I just mentioned, we're going to be using lines to approximate function values. So near x equals a, so this is the point of tangency that we're calling a f of a, the tangent line and the function f of x are close to each other. So near that point of tangency, the function itself and the tangent line, they're pretty close together. So the function f of x is approximately the tangent line. So this right here is really just the tangent line. We're used to writing our line as y minus y1 equals m times x minus x1. So here, this is simply just adding the y1 to the other side. So y is equal to y1 plus m times x minus x1. So y1 is f of a, m is our derivative at a, the slope of the tangent line, and then x minus a. So we're saying that the function is approximately this tangent line value near x equals a. Let's jump into an example. Let's say we're given the function f of x equals sine x. We want to write an equation of the tangent line at x equals pi, and we're going to denote it L of x. So let's just start right there. Write an equation of the tangent line at x equals pi. So to find an equation of a tangent line, we always need a point and a slope. Well, our point, half of our point anyways, is the x value pi. So to find the y value of the coordinate point, we're going to plug pi into our function sine x. So our point is pi sine of pi. And sine of pi is 0. Whoops. So this should be pi 0. And to find our slope is going to be f prime of pi. Our slope is going to be the derivative evaluated at pi. So we need to find f prime of x. F prime of x is cosine x. So f prime of pi, that's cosine of pi. And cosine of pi is -1. So we have our point pi 0, that's like our x1, y1, and our slope is -1. So our equation of a tangent line is y minus 0, y minus y1, equals slope m, -1, times x minus x1, which is x minus pi. So here is our equation of a tangent line, but we want to go ahead and solve it for y. And so here it's nice because this is just -0, so it basically is kind of solved for y, but if there was a value here, we would want to go ahead and add it to the other side because we're told to denote it, the line, as L of x. So in order to write L of x equals, we need to solve this equation for y. So here, y is negative 1x minus pi. So we're told to call it L of x. So L of x is negative 1x minus pi. All right, so that was the first part of the problem. Write an equation of a tangent line. Really nothing new about this process. We are just making sure to solve it for y and then call it L of x. Now in the second part, we're going to use the tangent line to approximate f of 3. So let's go ahead and take a look at our graph now for a second. So the problem also says label f of 3 and mark the approximation of L of 3 on the tangent line. So we're actually going to do that first, and then we'll use our tangent line to approximate f of 3. So f of 3 is plugging 3 into the sine function. So f of 3 is actually finding this value right here. But without a calculator, I don't really know what that value is, f of 3. Right? I don't know what sine of 3 is. So what we're going to do is we're going to approximate f of 3 by plugging 3 into the tangent line. So this blue line here, this is L of x, the line that we just found. So we're going to plug 3 in just a second into that line. So if I plug in 3, right, then I'm actually finding this value right here. So they're pretty close together, right? It's not too bad. Because I'm not that far away from pi. So pi is the point of tangency right here. And so as long as I'm not too far away from my point of tangency, then the actual function value and the approximate function value will be pretty close together. So let's go ahead now and find L of 3. So that's negative 1 times 3 minus pi. So that's going to be negative 3, right, plus pi. And we know pi is approximately 3.14. So negative 3 plus 3.14, that's approximately 0.14. So without a calculator, right, we were able to approximate the value of sine of 3. So L of 3 is approximately sine of 3. Right, which is f of 3. So our linear approximation at 3 is an approximation for the actual sine function, which I wouldn't be able to really do without the use of a calculator. So this whole process is called doing a linear approximation. That's what we just did. The linear approximation of f at a is just a tangent line that we use to approximate f near x equals a. Because hopefully you could see as we get further away from that point of tangency. So now as we move ourselves over here, if we were to try to use an x value that's now farther away from pi, the error is going to be much bigger, right? So I'm looking for an output on the sine graph. I would be getting an output on the, whoops, that wasn't right above it, but I'd be getting a value on the line, and there's a bigger error. So we just want to make sure we're near that point of tangency. This linear approximation, it's often denoted L of x, and sometimes a tangent line approximation, and sometimes it's called a tangent line approximation, or there's kind of a fancy word for it, a linearization. So basically all of those words are used interchangeably. A linear approximation of f, or a tangent line approximation, or a linearization. Let's look at another example. Use a linearization to approximate the square root of 3.9. So again, linearization is finding a tangent line approximation or a linear approximation. So we need to find a tangent line. But to what function? Well, the function that we're really dealing with here is f of x is equal to the square root of x. And we also need a point of tangency. So the point of tangency needs to be a value that we can actually substitute into the square root of x that's close to 3.9. Well, that value, of course, is going to be 4. So our a value is going to be 4. So now let's go ahead and find our point and our slope. So our point is going to be 4f of 4, or 4 and then the square root of 4, which is 4, 2. And then our slope is going to be f prime of 4. So let's go ahead and find f prime of x. So we have f prime of x. Well, that's 1 over 2 radical x. So remember, x is x to the 1/2. So we have 1/2 x to the negative 1/2. So 1 over 2 rad x. So we're looking at 1 over 2 times the square root of 4, or 1/4. All right, so now we have our point, we have our slope. We'll plug it into point-slope form of a line. So we're looking at y minus y1, so y minus 2, equals slope m, which is 1/4, x minus x1, so x minus 4. So here is our tangent line, but we have to solve it for y, which means we essentially just have to add the 2 to the other side to turn it into a linearization, right? Because we are going to use it in just a second to approximate the square root of 3.9. So we're going to add the 2 to the other side. So 2 plus 1/4 times x minus 4. So now this is a linearization. So basically what we know is that our function f of x is approximately this linearization L of x, which is that 2 plus 1/4 times x minus 4. So we want to approximate the function at 3.9. So f of 3.9 is approximately L of 3.9, which is 2 plus 1/4 times 3.9 minus 4. So let's keep going. We have 2 plus 1/4 times, okay, and here 3.9 minus 4, that's negative 0.1, right, or negative 1/10. I'm going to express it as a fraction. So I have negative 1/10 here. So that's the change in x, right? So negative 1/10. So we have 2 minus 1 over 40. And that should basically make sense. I'm still going to finish this out, but I just kind of want to point out how, we know the square root of 4 is 2. So the square root of 3.9 should be a little smaller than that. So, it's approximately smaller by 1/40th, which as a decimal, so this is 2 minus 0.025. So it's 1.975. That is an approximation for the square root of 3.9 using a linearization, using a tangent line. Now, if any of that last example felt sort of familiar, it's because it should resemble the process of using differentials. So we're going to do that exact same problem as the previous one, using differentials. We're going to use differentials to approximate the square root of 3.9. So what we need is we still need the function. So the function that we're working with is the square root of x, and we still need that a value. And so the a value is still 4. It still needs to be, the value I can actually plug into the square root function and be able to evaluate that's near 3.9. But for differentials, remember that we needed that value of delta x or dx, right? Those are both the same thing. So basically, how far away am I from 4, from 3.9? So I'm 0.1 away, but I'm 0.1 less than 4. So my value of dx is negative 0.1. All right, so now that we have all this information, we're going to go ahead and calculate the differential dy. So remember, dy dx, that's the derivative, which we've done a few times now. The derivative of radical x is 1 over 2 rad x. We'll multiply by the dx, so dy is 1 over 2 rad x dx. So now we're going to substitute in our a value and our dx value into our dy. So dy is 1 over 2 times the square root of 4 times negative 0.1. Well, that's 1/4 times negative 1/10, or that negative 1 over 40, or negative 0.025. So should be feeling kind of familiar, right? So this is the differential. This is the change in y. So when I change the input of the square root function, when I change it from 4 and I reduce it by a little bit, by 0.1, that's going to change the y value approximately by negative 0.025. So what's the approximate value for the square root of 3.9 then? So the square root of 3.9 then is approximately, right, the square root of 4 minus 0.025, minus that differential. Well, the square root of 4, right, is 2 minus 0.025. So there's that 1.975 value that we found from the linear approximation previously, right? So it is two different ways of accomplishing the same thing, and they're really not that different. The only thing that's sort of different is the notation. So let's try and see the connection, especially between those last two examples. To approximate the function f at x sub 1, that is a distance, delta x or dx, away from a, we can use either differentials or a linearization. So to find f of x sub 1, so that's just f of some a value plus some little distance away, right? F of a plus some small change in x. Well, that's going to approximately be f of a, so the output at the point of tangency, plus dy, the change in y, the approximate change in y. So we can approximate a function's value if we calculate the differential dy and then just add the output of the point of tangency, f of a, and then plus that small change in y. Or we can use a linearization. F of x sub 1 is approximately the linearization at x sub 1. So the linearization at x sub 1 is just the tangent line solved for y. So f of a plus f prime of a times x minus a. So I want us to notice the similarity here. So using differentials, it's f of a plus that small change in y, dy. Well, over here we have f of a plus this part here is technically dy. It's f prime of a times x minus a, and x minus a is the change in x, which is dx. So this is essentially a differential. This piece of a linearization is really just the differential dy. So let's look at a final summary of differentials and linear approximation. Differentials help us approximate the change in a function, whereas linear approximations, also called linearizations or tangent line approximations, those help us approximate a function's value. So differentials, we need to be given y equals f of x, and then we can compute the approximate change in y, dy, by doing f prime of x times dx. And again, dx is the same as delta x. Delta x is the actual change in x. And then delta y is f of a plus dx minus f of a. This we can usually find, or we need to usually find with the calculator, where delta y is the actual change in y. So the differential is just the change in the function, or an approximate change in the function, but we can use it to approximate a function's value if we just add that change in y to the output in the point of tangency. But if we're looking to approximate a function's value, we can also just go straight to linear approximations. We can find a tangent line, solve it for y, and then just plug in that value that we're trying to approximate in the original function. So we use a linearization to approximate f of x near x equals a. It's just an equation of a tangent line. It's nothing new. It's just that y minus y1 equals m times x minus x1 situation solved for y, right? So that sort of wraps it up, and it's really important to understand the difference between the two, but also how they connect together, and just understanding that notation.